Have you ever wondered about where it all began, the origins of the universe, the birth of time, space, and matter? Indeed, the cosmos is an enigma that has fascinated humanity for eons. From our ancestors gazing at the stars, from primitive dwellings to the modern astrophysicists peering into the depths of the universe through powerful telescopes, our curiosity remains unquenched. We yearn to unravel the mysteries that shroud our cosmic home. The questions are profound, the answers elusive. Yet, we've made astounding strides in our understanding of the universe, each discovery adding another piece to the grand cosmic puzzle. Our journey to understand the universe has been marked by many a theory, but none as compelling or as widely accepted as one particular proposition. So buckle up, fellow cosmic voyagers, as we embark on a journey back in time to the very beginning of it all. Today we delve into the most accepted scientific explanation for these questions, the Big Bang Theory. So, what exactly is the Big Bang Theory? Well, it's a sort of cosmic detective story. Picture this. The universe, all of space, time, matter, and energy, compressed into a single infinitely dense point or singularity. This is the starting premise of the Big Bang Theory. It suggests that around 13.8 billion years ago, this singularity underwent an intense period of expansion, often referred to as inflation. This wasn't a typical explosion, but rather a rapid expansion of space itself. In the blink of an eye, the universe transformed from a singularity, smaller than the head of a pin, to an ever-expanding cosmos. The universe at this time was a hot, dense soup of particles and energy, too hot for atoms to form. As the universe expanded, it cooled. This cooling process allowed for the formation of protons and neutrons, the building blocks of atomic nuclei. The Big Bang Theory is not just a tale of origins, but also a narrative of evolution. It details how the universe grew from this fiery, dense state to the vast, cooler cosmos we observe today. It explains the birth of the universe and its subsequent expansion, a process that continues even now. You see, the beauty of the Big Bang Theory lies in its simplicity and its power. It takes us back to the very beginning of time and space, to the birth of all matter and energy. It's a story of cosmic proportions, one that has shaped our understanding of the universe and our place within it. But how do we know all this? What evidence do we have to support these incredible claims? We'll delve into that in the next section, where we'll explore the observational evidence that supports the Big Bang Theory. For now, just remember this. The Big Bang Theory is the cornerstone of modern cosmology. It's our best scientific explanation for how the universe began and how it has evolved over billions of years. This theory not only explains the birth of the universe, but also its subsequent expansion. The universe is expanding, but what does this mean? Well, let's delve into it. The idea of an expanding universe is central to the Big Bang Theory. It suggests that the universe, which started from a singularity, a state of extreme heat and density, has been expanding ever since. But how can we be sure of this expansion? The answer lies in the light from distant galaxies. When we observe this light, we notice something fascinating. The light appears redder than it should be. This phenomenon, known as redshift, occurs because as a galaxy moves away from us, the light it emits is stretched into longer and thus redder wavelengths. It's like hearing the pitch of a car engine drop as it speeds past you. This is the Doppler effect, a change in frequency and wavelength of a wave in relation to an observer who is moving relative to the wave source. In the case of the universe, the car is a galaxy, and the sound it's making is light. From a hot, dense singularity to the vast cosmos we know today, how did the universe evolve? Let's journey back to the very early stages of the universe, right after the Big Bang. At this point, the universe was a seething cauldron of energy and matter, too hot and dense for anything to exist in a stable form. Yet as the universe expanded, it cooled. And in this cooling universe, the first elementary particles began to take shape. Quarks, electrons, neutrinos, and their antimatter counterparts emerged from the energy soup. Over time, as the universe cooled further, these quarks came together to form protons and neutrons. But the universe was not yet a place where atoms could exist. It was still too hot, and any atoms that tried to form were immediately blasted apart by high-energy photons. This era, aptly named the photon epoch, was a time of atomic turmoil. However, as the universe kept on expanding and cooling, there came a moment about 378,000 years after the Big Bang when atoms could finally form. This event is known as recombination. Electrons combined with protons to form the first hydrogen atoms, the building blocks of everything we see around us today. Now, with atoms in place, the universe was ready for the next stage of its evolution. It was time for the cosmos to light up. The first stars began to form, igniting the cosmic dark ages. These stars grouped together to form galaxies, and galaxies assembled into clusters, creating the cosmic structures we observe today. From a singularity to a universe teeming with galaxies, the journey of the cosmos is truly fascinating. Each stage of the universe's evolution, from the formation of elementary particles to the creation of cosmic structures, is a testament to the power and complexity of the cosmos. The Big Bang Theory provides a roadmap to the evolution of the universe. But how do we know all this? What evidence do we have? To answer these questions, we look to the stars. The cosmos, in its silent majesty, provides us with a treasure trove of clues. One of the most significant pieces of evidence supporting the Big Bang Theory is the cosmic microwave background radiation, or CMB. This is the afterglow of the Big Bang, a faint whisper of radiation that permeates the entire universe. It's a snapshot of the universe as it was about 380,000 years after the Big Bang, when it had cooled down enough for atoms to form and photons to travel freely. The CMB is remarkably uniform, but it has tiny temperature fluctuations that reveal patterns that match the predictions of the Big Bang Theory. This radiation is like a cosmic baby picture, showing us the universe in its infancy. But there's more. The Big Bang Theory also predicts the abundance of light elements in the universe. In the intense heat of the early universe, protons and neutrons collided to form hydrogen and helium, the lightest elements. And the proportions of these elements we observe today, about 3/4 hydrogen and 1/4 helium by mass, align beautifully with the predictions of the Big Bang Theory. Finally, let's look at the distribution of galaxies. The universe isn't a cosmic jumble. Instead, galaxies are strung out in vast filaments and walls surrounding immense voids. This cosmic web is a direct consequence of tiny quantum fluctuations in the early universe, magnified over billions of years by the force of gravity. And again, this is just what the Big Bang Theory predicts. So when we ask, what evidence do we have for the Big Bang, we can answer, just look up. The stars, the galaxies, the very fabric of the cosmos all bear witness to the Big Bang. It's a theory that not only explains what we see, but also predicts what we should see. The cosmos speaks to us, and its message supports the Big Bang Theory. So, what have we learned about our cosmic beginnings? We've traversed the fascinating path of the Big Bang Theory, the most widely accepted scientific explanation for the genesis of the universe. We learned that it all started around 13.8 billion years ago, from an incredibly hot and dense singularity. We've seen how our universe expanded, and how this expansion is supported by observational evidence like the redshift of galaxies. We've journeyed through the early stages of the universe, witnessing the formation of elementary particles, atoms, and cosmic structures. We've marveled at the birth of the first stars, galaxies, and galaxy clusters over cosmic time. We've looked at astronomical observations such as the cosmic microwave background radiation and other evidence like the abundance of light elements and the distribution of galaxies. The Big Bang Theory, a remarkable scientific insight into the origins and evolution of our universe. Don't forget to subscribe for more enlightening content on science and cosmology.